In basic thermodynamics, in the topic of work done, we have to study two types of work done. First, displacement work. Second, flow work. So first of all, we are going to discuss displacement work. Now, as name is suggesting that something is getting displaced, right? So that's why name is displacement work. So what is the basic formula of work done? Basic formula of work done is force multiplied by displacement in the direction of force, right? Displacement, right? This is the basic formula, correct? Now to understand the displacement work thoroughly, let's take the example of piston cylinder assembly. So we have piston cylinder assembly here, in which we have gas at high pressure, right? Cross-sectional area of piston is A, right? Now, let's say this is the initial position of the piston, right? It is at state 1, correct? Now, let's say because of this high pressure gas, piston is getting pushed, piston is getting displaced by small amount dl, right? By small amount dl. So what will be the work done in that case? Work done in that case, it will be force multiplied by displacement dl, right? That will be the work done, correct? Now this force can be written as pressure multiplied by area. Pressure into area. So we will substitute there. What we will get? Pressure into area into small elemental length dl, correct? What is area into length? Area into length, that is volume, right? So this is small elemental length dl. So it will be elemental volume dv, correct? So this will be pressure P into dv, small elemental volume dv. We are denoting the volume by symbol V, right? So this will be small differential volume dv, that is area multiplied by small elemental length dl. This will be the work done then, right? In pushing the piston by very small amount dl, this will be the work done. Now let's say if piston is moving from state 1 to state 2 like this, then what will be the work done? Work done will be, we have to integrate it. We have to integrate it from state 1 to state 2. So this will be P dv integration 1 to 2. This will be the expression for displacement work done, right? Now let's see one interesting thing. Now again we have piston cylinder assembly. Now we will draw the path on PV plane, pressure volume plane, right? We can measure the pressure and then we can find out the volume, right? Then again when system is changing its state, we can measure the pressure and volume and we can plot it. When we will connect locus of all the point, then we can draw the path on pressure volume plane, right? And that path will be, let's say that path is like this. Right, when piston is getting displaced from state 1 to state 2, right? Let's say initial volume at state 1 is V1, final volume at state 2 is V2, right? Now let's consider one small element of width dv. This is the small element we have considered. Let's say width of this is dv, right? And we consider this at particular pressure, let's say pressure P. At pressure P we have considered it, correct? Now what will be the area of this small element? Area of this will be area of rectangle, that is length into breadth, right? So area of this will be P into dv. This will be the area, correct? Now if I want to find out complete area under this path from state 1 to state 2, this will be the complete area. So how I can find out? We have to integrate it from point 1 to point 2. But this is the work done. Just now we have proved this is the work done, correct? It means that we can write work done is also the area under PV curve. Correct? Work done can also be found by finding out the area under PV curve. Correct? So this is the important conclusion we can draw from here. We can find out the area under PV curve, and that will be equal to work done. Right? Now coming to the process, for example, we have constant pressure process, right? Also known as isobaric process. So let's say process is happening such that pressure remains constant, correct? Pressure remains constant. So how we can find out the work done? We have the formula, work done is equal to integration 1 to 2 PdV, right? So pressure is constant, so we can take this P outside of integration. We can write like this, correct? What will be the integration of dV? It will be simply V. P integration of dV will be V limit 1 to 2, right? So we can write pressure upper limit minus lower limit V2 minus V1, right? This will be the work done expression. Work done is equal to P V2 minus V1. This will be the work done for constant pressure process, right? Constant pressure process. Now coming to the path on PV plane, pressure volume plane, how we can draw constant pressure line? That will be horizontal line, right? Such that pressure remains constant. That line will be like this, correct? It shows constant pressure. Where volume is changing, pressure remains constant, correct? So if we want to find out area under this, how we can find out? This will be initial state, volume V1, final volume is V2. If we have to find out area under this PV curve, that will be this area. How we can find out this area? It is simply area of rectangle. What is the area of rectangle? Area of rectangle is this thing multiply by this, right? This is, let's say, at particular pressure P. Particular pressure P. So this is P. What will be this length? From here to here, what will be this length? That is V2 minus V1, correct? So area of rectangle will be P multiplied by V2 minus V1, right? That is work done, and this is what we already got. This is what we already got. Correct? Okay. So next process is constant volume process, also known as isochoric process. So again we have to use same formula. Work done is equal to integration 1 to 2 PdV, right? For constant volume process, what will be change in volume dV? Change in volume dV, that will be 0 because volume remains constant for constant volume process. So if dV is 0, if this is 0, work done will be 0. And that has to be 0 because we are discussing displacement work done, right? If volume remains constant, it means that piston is not getting displaced, correct? So if it is not getting displaced, work done will be 0. Without even finding out, we can write that, right? Work done will be 0 for constant volume process because there is no displacement, right? How the line will look like on pressure volume plane? It will be vertical line such that volume remains constant and pressure will change. It will be like this. So no area under this, right? So that's why work done will be 0. Displacement work done will be 0 for constant volume process, isochoric process. Correct? Now third process is constant temperature process, also known as isothermal process. So again we need to apply same formula of work done, that is work done is equal to integration 1 to 2 PdV, right? Now we have to integrate it. How we will integrate? From equation of state we know that PV is equal to mRT, right? For closed system, mass is constant, so this is constant, right? R value for given gas, characteristics gas constant, it is also constant for given gas. For example, let's say air is given or nitrogen is given, right? For given gas, R will be constant, characteristics gas constant will be constant. And we are dealing with constant temperature process, so T is also constant, right? So this entire thing is constant, right? So we can write PV is equal to constant. We can write this, correct? PV is equal to constant. From here we can write P1 V1 is equal to P2 V2, right? From this expression, what will be P? P will be C divided by V. C divided by V. So P1 V1 is equal to P2 V2 is equal to constant. Both are equal. So now we are going to replace P using this expression. We will put here, right? When we'll put here, what we will get? Integration 1 to 2. In place of P, we will write C by V. In place of P, we will write C divided by V into dV. C is constant, we can take it outside of integration, right? C integration 1 to 2 dV divided by V. What will be integration of 1 by V? Log V, ln V, right? So ln V, limit 1 to 2, correct? So what we can write then? C ln upper limit minus lower limit ln V2 minus ln V1. Using property of the log, we can write it ln V2 divided by V1, right? So we can write it C ln V2 divided by V1. Now in place of C, we can write P1 V1, P1 V1 or P2 V2 also. So let's write P1 V1. So we will get the work done formula, that is P1 V1 ln V2 by V1. This will be the work done formula, right? This formula is in terms of volume ratio V2 by V1, right? We can find out work done formula in terms of pressure ratio also. From this expression, P1 V1 is equal to P2 V2. P1 V1 is equal to P2 V2. We can write V2 by V1 is equal to P1 by P2. P1 by P2. So we can replace this V2 by V1 in this work done expression, V2 by V1, in terms of pressure ratio, right? So when we will replace, what we will get? Work done is equal to P1 V1 ln P1 by P2. Correct? This will be the work done formula in terms of pressure, right? How constant temperature process will look like on pressure volume plane? We have this relation between pressure and volume, this relation. PV is equal to constant, right? So pressure is equal to C by V. Pressure is inversely proportional to the volume. When volume increases, pressure will decrease. When volume decreases, pressure will increase. So how line will look like? It will be like this. Correct? So this is V1, initial state volume V1, final volume V2. So the work done expression which we found in terms of volume ratio or pressure ratio, this work done is in fact area under this curve, right? So this is how we have to find out work done for different process. Correct? Now let's see the sign convention. Sign convention for work done. So again, we have piston cylinder assembly. So let's say this gas is at high pressure, and because of that this gas will expand, it will push the piston upward, right? When this will push the piston upward, volume will increase. So this system will give us work done, right? So during expansion volume will increase, system will work for us, right? So when system is working, that we will take as positive. So this will be the sign convention which we will follow throughout the course. So work done is positive when system is working. Right? So we will take it as positive. Correct? Now when we are compressing the gas, let's say we are pressing the piston and we are compressing this gas, right? Then volume will decrease. So we are working on the system, right? When work is done on the system, then that we will take as negative, right? In this case, volume will decrease, we are compressing the gas, volume will decrease and pressure will increase, right? That we will take as negative. When work is done on the system. When work is done on the system. correct? So when system is working, that will be positive. When we are working on the system, when work is done on the system, that will be negative, right? Sign convention is clear. We have to use this sign convention throughout the course. Now let's solve few problems. 1 kilogram of air initially at temperature of 127 degrees Celsius. So we have mass equal to 1 kilogram initially at temperature of 127 degrees Celsius. So what will be T1? T1 will be 127 degree Celsius. So in Kelvin, what will be temperature? That will be 127 plus 273, that is 400 Kelvin. This will be initial temperature T1. It expands reversibly at constant pressure. So pressure remains constant, right? So pressure remains constant. Pressure is equal to constant, means P1 is equal to P2, correct? Until the volume is double. Until the volume is double. So V2 final volume will be 2 times of initial volume. If gas constant of air is 287, so R value, characteristics gas constant, is equal to 287 joule per kilogram Kelvin. The magnitude of work transfer is, we have to find out work done. So what is the formula of work done? For constant pressure process, work done is equal to P V2 minus V1, correct? P1 is equal to P2, so that's why we have written simply P. This will be equal to P. V2 is 2 times of V1 minus V1. So work done will be equal to P into V1. Now using equation of state, we can write P1 V1 is equal to mR T1, correct? So P1 is equal to P2 is equal to P. So value of P into V1 is equal to mR T1, correct? So let's substitute. Work done is equal to mR T1. Now let's substitute the values. M is equal to 1 kilogram. R is 287. T1 is 400. Remember, whenever you are substituting the values, it should be in SI unit. Whenever you are substituting values in the formula, it should be in SI unit. So SI unit of temperature is Kelvin. So that's the reason we have to substitute temperature in Kelvin. We can multiply this. We will get work done is equal to 114800 joule, right? They are asking in kilojoule. They are asking in kilojoule. So we can divide it by 1000. 114800 divide by 1000. It will be in kilojoule. So answer will be work done is equal to 114.8 kilojoule. This will be the answer, correct? 114.8 kilojoule. So this was the example of constant pressure. We had to find out work done for constant pressure process, correct? Now let's see next example. A cylinder contains 5 meter cube of an ideal gas at a pressure of 1 bar, right? So volume V1 is equal to 5 meter cube. Pressure P1 is equal to 1 bar. 1 bar means 10 raised to power 5 Pascal or Newton per meter square. gas is compressed in reversible isothermal process. So this process is isothermal process till its pressure increases to 5 bar. So we are compressing the gas by isothermal process. So P2 will be 5 bar. That is 5 into 10 raised to power 5 Newton per meter square. So Newton per meter square or Pascal, it is SI unit of pressure. The magnitude of work in kilojoule required for this process. Again in kilojoule we have to find out work done. So this is isothermal process. So what is the work done formula? What is the work done formula for isothermal process? That is P1 V1 ln P1 by P2 in terms of pressure, because we have P1 and P2 value. So we can substitute the values now. P1 is equal to 10 raised to power 5 into V1, that is 5 ln P1 by P2. So P1 is 10 raised to power 5 divided by P2, 5 into 10 raised to power 5. This will get cancelled out. We can find out. So after finding out, we will get minus 804719 joule. They are asking in kilojoule, so we have to divide it by 1000. Minus 804719 divided by 1000. So what we will get? Minus 804.719 kilojoule. This will be the answer. But they are asking magnitude of work. Why we are getting the work done in negative? Because we are compressing the gas, right? We are compressing the gas. We are doing the work done on the system. That's why it is negative, right? But they are asking only magnitude. So answer will be 804.7 kilojoule. So option A. Correct? Like this we have to solve the problems. So first of all you have to see which process is given in the question. According to that process you have to apply the formula. Let's see one more example. A piston cylinder device initially contains 0.4 meter cube of air to be treated as an ideal gas. So initial volume V1 is equal to 0.4 meter cube. At this much pressure, 100 kPa. So P1 is equal to 100 kilopascal, means 10 raised to power 3 Pascal, that is Newton per meter square, and 80 degree Celsius. So temperature T1 is equal to 80 degree Celsius. What will be temperature T1 in Kelvin? T1 is equal to 80 plus 273. Correct? That will be equal to 253 Kelvin. Right? Air is now isothermally compressed. Again we are compressing. By which process? Isothermal process. Isothermal means temperature remains constant. Correct? Means temperature will be constant. So T1 is equal to T2. So it is now compressed isothermally to this much volume. Means V2 will be 0.1 meter cube. Correct? Work done during this process is in kilojoule. We have to find out. So again for isothermal process, work done formula is P1 V1 ln. Now we have V1 and V2 both. Here V1 and V2 both. So we can apply the formula in terms of volume ratio ln V2 by V1. Now we can substitute the values. Pressure P1 100 kilopascal, multiply by V1 0.4 ln V2 by V1. V2 is 0.1, V1 is 0.4. We can calculate this. We will get work done is equal to minus 551.76 joule. They are asking in kilojoule. So what will be answer in kilojoule? We need to divide it by 1000. Divided by 1000. So we will get minus 55.451 kilojoule. This will be the answer. Correct? Now if you understood this, I am giving you one homework problem. A frictionless piston cylinder device contain a gas initially at this much pressure. So this is P1, 0.8 megapascal. So P1 is equal to 0.8 megapascal. Mega means 10 raised to power 6. So 0.8 into 10 raised to power 6 Pascal or Newton per meter square. And volume is also given. V1 is given 0.015 meter cube. It expands quasi-statically at constant temperature. Again constant temperature, so isothermal process it is. To a final volume of this much. So final volume is also given. V2 is given 0.030 meter cube. Correct? The work output in kilojoule during this process will be. So we have to find out work done. For which process? For constant temperature process. So whenever you are solving any problem, first of all see which data is given and then see the process. Check the process, which process is given, which process is mentioned in the question. According to that you have to choose the formula. So for constant temperature process, you know the work done formula is P1 V1 ln V2 by V1. So everything is mentioned, just substitute the value and find out the answer. They are asking in kilojoule. Find out the answer in kilojoule. Right? Now if you understand everything, like how we are finding out the work done, what is the basic formula of work done, then I am giving you one homework to find out the expression, to derive the expression of work done for a process where pressure varies linearly with respect to the volume. Like this. You need to derive an expression for work done for a process where pressure varies linearly with respect to the volume. Right? This is the homework from my side. If you understood everything, this is the homework from my side. And I am giving hint also. What will be the final answer for this? That will be the area under this curve. What will be the area under this curve? This will be the area. And obviously this area is the summation of area of this triangle plus area of this rectangle. Right? This will be the final answer. So you can derive the expression for work done for this kind of process where pressure varies linearly with respect to the volume. This is the homework from my side. In next class, we will be discussing this derivation and then we will find out work done for isentropic process, work done for polytropic process, then we will compare work done for all the process, right? That we will discuss in next class. Now we are starting new batch from 12th July, that is from today. We are starting new batch for GATE Aerospace 2026 and 27. If you are interested, you can join this batch. You can take the feedback from your friends or the students who are studying here. You can freely take the feedback regarding teaching, and then you can make the decision of joining.